This video is for lesson 33-1. We're going to investigate two different kinds of three-dimensional figures, prisms and pyramids. Learning goals are to look at the properties and cross-sections of prisms and pyramids, and to figure out relationships among the faces, edges, and vertices of any polyhedron. A polyhedron is a three-dimensional solid figure. One vocabulary word that we'll use in this lesson is the word net. In geometry class, a net is a two-dimensional pattern drawn on paper that can be cut out and folded up to make a three-dimensional figure. The solid lines in a net are where you would cut with scissors. The dashed lines in a net are where you would fold. One geometry skill is to be able to imagine what a shape would fold up into. So what do you think this first net would fold up and create if you fold the ends upwards and then fold these rectangular flaps over? This makes a shape called a triangular prism. What do you think figure 2 makes when you fold that net? When you fold these triangle flaps upward to touch at a point in the middle, that would make a pyramid. So that first net would fold up and create a three-dimensional shape called a prism. A prism is a three-dimensional solid with two congruent polygon parallel bases. The other faces of the three-dimensional shape are called the lateral faces. Here's some follow-up questions about that first net. What is the shape of the two congruent parallel bases? So looking back at this figure, there are two triangle faces and there are three rectangles. Which of those, when it's folded into a three-dimensional shape, would be the congruent parallel polygons? That would be the two triangles. Next question, what is the shape of the three lateral faces? Those are the rectangles. Next question, what would you call that shape when the net is folded up? Again, you have to imagine what this looks like in three dimensions. The triangle would become one of the ends, and then we have the rectangle lateral faces, and then the back end would also be a triangle. I'm trying to draw an illusion of what the three-dimensional object would look like. To name this, we name it according to what shape the bases are. We would call this a triangular prism. Next question, what's the difference between a right prism and an oblique prism? In a right prism, all of the lateral faces are rectangles. In an oblique prism, some of the lateral faces will be parallelograms. Contrast these two triangular prisms. Here's my first prism. Here's my next prism. One of these is a right prism and the other is an oblique prism. Which one's a right prism? It's the first one. This one here is oblique. It's like it's been smushed or tipped a little out of whack. The second net from the other page of this packet folds up into a pyramid. A pyramid is a three-dimensional solid with one polygon-shaped base, and the lateral faces are triangles that meet at a common vertex, the top of the pyramid. Pyramids are named according to the shape of their base and whether they are right or oblique. If you were to take the net from the first page and fold it up, it would create a pyramid shaped like this. This is a right pyramid. This one over here is oblique. Again, notice it kind of looks like it's been smushed over or knocked out of whack. Both of these pyramids are called square pyramids because the shape of the polygon base is a square. Next, skip down to question 4. The figure drawn below is a hexagonal pyramid. That name tells us what shape the base is. The root word of hexagonal is a hexagon. There are some follow-up questions about this shape. What are the vertices of the pyramid? Vertices is the plural of the word vertex, and it refers to the corner of the shape. So there is point T, which is the top of that pyramid, but also points A, B, C, D, E, and F. These vertices are all at the bottom of the pyramid around that hexagon-shaped base. Next question, what are the base edges? Edges are the segments that connect the vertices. For base edges, we want to list all the segments around the base. So the pyramid is standing on the base the way that it's drawn right now. One base edge is the segment from A to B. So we would name that segment AB. The base edge that's closest to our bodies goes from B to C, segment BC. I'm going to pause the video for you to name the rest of the base edges. And here are all 6 of the answers. Recall that the base is a hexagon which has 6 sides, so we have to have 6 segments listed or we forgot some of them. Now next question, list the lateral edges. The lateral edges of a pyramid are the segments that go from the base up to the vertex of the pyramid. One of them goes from point A along this edge all the way up to point T. That is segment AT. Another lateral edge of the pyramid goes from point B up this line to point T. That is segment BT. I'm going to pause the video for you to list the rest of the lateral edges. And here are all 6 of the segments that are the lateral edges. Again, if the base has 6 vertices, then there must be 6 lines running from the base up to the top point of the pyramid. You have to have 6 lateral edges, or you forgot some. Next, question D. List the lateral faces. This pyramid has 7 faces. The bottom is the base, and it's a hexagon. But what are all the lateral faces? All of the sides of the pyramid? They are triangles. So when you name them, you would name them as triangles. For example, triangle BCT. In the way that this pyramid is drawn on paper, triangle BCT is the front face, the one that is closest to our bodies. Traveling around the pyramid in this direction, the next face that we reach is this one here that I'm shading in purple. How would you name that triangle? It's CDT. So you would say triangle CDT. I'm going to pause the video for you to name the rest of the triangles. And here are the 6 lateral faces listed. I know that there are 6 of them because the base was a hexagon. If the base has 6 sides, then each of those sides will extend upward to the top point of the pyramid. There will be 6 lateral faces. Now move to question 5. We're going to complete the table. In this table, we have names of different prisms and pyramids, and it asks us how many faces do these shapes have, how many vertices, and how many edges. The first one we're asked is a triangular prism. We had a drawing of that on an earlier page. Over here on the left, however, I'm going to draw another one so we have something to look at. Here's a triangle, and then it extends back into the distance, and then here is the back triangle. I'm using dashed lines to indicate hidden edges, edges that you have to make believe that you could see through the shape if the shape was translucent. So here's my drawing on flat paper of what's intended to be a 3-dimensional object called a triangular prism. How many faces does it have? Well, there are 2 triangle faces and 3 rectangles. It's sitting on one of the rectangles, and then we have a rectangle that is like closest to our eyes, and then we have a rectangle that I might call the back face of the shape. So it has 5 faces. How many vertices does it have? How many corners? Well, looking at the triangle here on the left, there are 1, 2, 3 around it, And then the back triangle would have 1, 2, 3. There are 6 vertices. Next, how many edges does it have? 3 around this triangle, 3 around the back triangle, and 3 of these long edges that go alongside the rectangles. There are 9 edges. Now the next question is a rectangular prism. Let's draw one. I'm going to draw a rectangle and then extend back into the distance with some edges. And then finish drawing the back of that rectangle. I'm also going to use dash lines to draw the hidden edges, the ones that you have to make believe that you could see if your shape was translucent. How many faces does this box have? It has 6. How many corners does a box have? It has 8. And how many edges does it have? It has 12. As we're filling out this table, we want to try to discover a relationship between the number of faces, number of vertices, and number of edges. Our next one is a pentagonal prism. I'm going to draw a picture of that. First, I'm going to draw a pentagon, a 5-sided polygon. Here is a pentagon. And then I'm going to draw some edges coming straight down. And finish off the bottom of the pentagon. Now using a dashed line, I'm going to draw that last edge downwards, and then this is a dashed, and this is a dashed. Again, I'm simply trying to create the illusion of a three-dimensional object drawn on flat paper. How many faces does this shape have? How many vertices does it have? And how many edges? I'm going to pause the video for you to count all those values. One of the things we're asked is how many vertices it has. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 vertices. Another thing we're asked is how many edges it has. Around the top, there are 5. Around the bottom, there are 5. And then there are 5 vertical edges. That's 15 edges. We're also asked how many faces it has. It has a top and it has a bottom. They're both pentagons. And then it has 5 rectangle lateral faces. So it has 7 faces. The next one we're asked to do is a square pyramid. Let's draw one so we have something to look at. To give it the illusion of 3 dimensions, even though the bottom is a square, when I draw the pyramid, I'm not actually drawing a square because that doesn't create the illusion that I want. So I'm going to draw a rhombus. And then I'm going to locate the exact center of the rhombus and move straight upwards from there to be the top of my pyramid. Then I'm going to draw my diagonal edges. By drawing a pyramid this way, this creates a much more realistic looking three-dimensional picture. Okay, now that you have something to look at, I'm going to pause the video for you to do faces, vertices, and edges. And here are the answer. 5 faces, 5 vertices, 8 edges. The last one that we have a name for is a pentagonal pyramid. The bottom of this pyramid is a pentagon, and then because it's a pyramid, it stretches up and touches at a single point. I'm going to pause the video for you to draw your best pentagonal pyramid that you can so that you can figure out the faces, vertices, and edges. Here is a drawing of my pentagonal pyramid. This has 1 bottom face and then 5 triangle-shaped lateral faces, so 6 faces. This has 5 vertices around the bottom and 1 at the top for 6. And then it has 10 edges, 5 around the pentagon base, and then 5 that stretch upward to that top point. The next row of the table is missing the name. Is it a pyramid or a prism? To answer this, we have to observe some patterns in the rows we've already done. One thing I notice is that when you add the faces plus the vertices, you get 2 more than the number of edges. 5 plus 6 is 11. That's 2 more than 9. 6 plus 8 is 14. That's 2 more than 12. 7 plus 10 is 17. That's 2 more than 15. The difference between prisms and pyramids seems to be that in prisms, the number of vertices is a larger number than the number of faces. 8 is more than 6. 10 is more than 7. But in a pyramid, the number of faces is equal to the number of vertices. 5 and 5, 6 and 6. So because the next row has 7 and 7, it is a pyramid. Now to name the kind of pyramid, we need to know the shape of the base. A pyramid has one base, and then all the rest of the faces are lateral faces. So if there are 7 total faces, and one of them is the base, then there are 6 lateral faces. This is a hexagonal pyramid. Next row. The faces is 8, the vertices is missing, and the total edges is 18. Remember that this 18 is 2 less than the sum of the faces and the vertices. So this here must be 12. 8 plus 12 is 20, and then the 18 is 2 less than the 20. Now we're able to name it. Because the faces is not the same as the vertices, this is a prism. To name what kind of prism it is, we have to know the shape of the base. A prism has 2 bases. So of the 8 faces, 2 of them are the bases. The other 6 of them are the lateral faces. This is a hexagonal prism. I'm going to pause the video for you to work on the last row of this chart. It didn't matter what you figured out first, but because 4 plus 4 is 8, this last number is going to be 6, because it's 2 less than the sum of the faces and vertices. Now, because this is 4 and this is 4, we know that this is a pyramid. To decide what kind of pyramid it is, we're going to take 1 less than the number of faces. This is a triangular pyramid. Question 6 says to identify any patterns we notice. One of the patterns we noticed is that the number of faces plus the number of vertices, take away 2, is equal to the number of edges. I'm using F to be faces, V to be vertices, E to be edges. Write the first row of the chart. 5 faces plus 6 vertices minus 2 equaled the 9 edges. That checks out, right? So this right here is a good formula to know when we're working with these 3-dimensional shapes. When we started the lesson today, we said that one useful skill is to be able to imagine folding up a net and figuring out what the 3-dimensional object would be. Another useful skill is to have a 3-dimensional object and be able to figure out what view you would have if you look at it from the bottom or top or side. For example, if we have a rectangular prism, a common box, what would this look like to you if you viewed it from the bottom? If your eyes were looking directly at the bottom and you could not see the sides of it at all, what shape would you see? You would see a rectangle. If you were looking at this from the top, what would you see? You would see a rectangle that's congruent to the rectangle on the bottom. If you were looking at it from, let's say, the right side, what would you see? You have to imagine that you're standing over here and you're viewing this side of the shape only. What would you see? You would see a rectangle. Skip to number 11. What is the bottom view, top view, and side view of a square pyramid? I'm going to pause the video for you to draw those views. And here are the answers. You can compare your drawings to mine. They don't have to be perfect, but you have to have the right idea. If you look at a square pyramid from the bottom, you would see the square bottom, and only that. If you look at a square pyramid from the top, you would see a square shape, but you would also see right in the center like a dot where the point of the pyramid is, and you would see those diagonal edges that came up to that point, and it would look like this. Now when you look at a pyramid from the side, you would see a triangle. There's one more vocabulary word in this section about three-dimensional shapes. The word is cross-section. A cross-section of a solid figure is the intersection of that figure with a plane. A cross-section is what you would see if you cut the figure, let's say with a knife. Let's say you had this triangular prism and you took a knife blade and you sliced it right through here. Right, you took a knife and you cut right through there. What shape is that cross section? It would be a rectangle shape. We're not studying cones today, but imagine what the cross section would be if you had a three-dimensional cone and you took a knife blade and you sliced right through the side like that. And then you tipped the thing up and looked at the shape you created. What shape would the cross-section of a cone be? It would look like a circle. Let's summarize. In this lesson, we discussed prisms and pyramids, which are two kinds of solid three-dimensional figures. Some of the vocabulary we use to discuss these shapes are faces, edges, vertices, lateral edges, or bases. We practiced drawing the top, bottom, and side views of these shapes, and we discussed how you can make a pattern called a net, which can be folded up to create the actual shape itself. Last, we discussed cross-section, which is the shape that's created when you slice through a three-dimensional object with a knife.